Gradient descent is an algorithm that numerically estimates where a function outputs its lowest values. Gradient descent is an optimization algorithm which is widely used in a lot of training a machine learning model. It is based on a convex function and tweaks its parameters iteratively to minimize a given function to its local minimum. It's one of the most widely algorithm, and we'll go in more detail. Now let's get into the intro.
Welcome to the OTech Talks podcast, where it's all about working on technologies. You will hear the latest tech information, and your host, Kashif Manzoor, brings together product overviews, how-tos, best practices, tips and tricks, and troubleshooting techniques.
Welcome to OTech Talks podcast. This is session number 72 after a break of almost 3 to 4 months. And your host, Kashif Manzoor, is with you. If you're new to the show, new to the podcast, Open Tech Talk is your weekly sandbox for technology insights, experimentation, and inspiration with the primary objective of learning and sharing. Last 3-4 months, there was a break. I was doing, as I already mentioned, a number of older podcasts that I have started MSc in AI, and that took me initial 6 months because they started in September. So the initial 2 modules were on mathematics and then Python for artificial intelligence. So right now I'm doing the mathematics for AI, and that's why gradient descent topic comes in my mind and as in one action item, and then I said to share with you my knowledge. And that took me a while to understand and get into tune my lifestyle along with office work. And I just want to reiterate it. The objective of this blog and the podcast, there were primarily two purposes or two objectives were to write about what I'm learning in my own words, and to share my perspective and reflection. So that the whole idea was to reinforce what I'm learning, and people and experts says that you don't know really until you can teach it, or you teach to someone, or you can share it with someone. It will reinforce the learning. And then another objective was to share my views, my reflections, what I found helpful for me, and share a snapshot of my views to the rest of my friends, colleagues, to the community where I'm spending my time from last 10 to 12 years, or more than that one, when I started even initially auraerp.com. That was a forum. It was started in 2000, I think 9 or 10. And from there onward, I used to write blogs. And these blogs are basically living document. So maybe sometime I will come back and edit things. And sometime I'll get lazy and I don't update it. But I try my best to keep updating these documents. And these are all informal posts, more of a quick brain dumps, rather than literary, or rather than any formal document or a study guide. So that's what I started again. So now I'm going to share primarily on 3 topics, because one topic is where I work as a cloud architect or solution architect with enterprise vendor or Oracle. So, and I'm from day one as a career, I was doing, Oracle stuff from DBA to developer to consultant to all the management roles. So my focus will be on what I'm learning on the Oracle side, on Oracle Cloud Infrastructure. And nowadays I'm focusing on Oracle Cloud Infrastructure. That's the one with the main topic which I'm going to do it. And then the second is which I'm right now doing the MSc AI. And I thought to share with you whatever I'm learning with respect to machine learning, or whatever the subjects that keep coming, and some interesting topic. So that's the main focus on the second area. And the third area is overall digital transformation, because end of the objective, or the objective is that, okay, either we use AI or these vendors or applications, enterprise or infrastructures. We want to solve the business problems, and we want to make sure that the world and the solutions are for the humanity. So the transformation which we're going through, even with this COVID-19 and pandemic and all that, the digital transformation. So that will be the third area which we'll be talking on it. So these three areas we're gonna discuss in our podcast and on my blogs. And this blog is primarily a journal, and I know this podcast is taking a long time in the opening before I go to the actual topic, but it's like a journal, and the content are most of the public content where I write something and then it enforces me that, okay, I need to follow it. You can, these are comments and these are my views, so you can disagree with that, and you can share your views. So let's have a discussion on that. And it's an open tech talks. That's why I'm a believer strongest believer on the open talks, and open to listen to your ideas, and we can have a chat, we can have a discussion on it. So feel free to share your views, and I'm still, thank you so much from long time. I think this podcast is running more than 5 years, and overall I'm doing blogs more than 10-12 years. And I'm very thankful to you, to your sharing with me a lot of feedbacks and comments, and it's a good. And I've made so many friends during this time. And with the podcast, we are going good. I think the last time I checked, a couple of months back, the statistics we were crossing at that time 25K plus downloads, and that's quite handsome or quite good. From my point of view, that people are listening. And another day, someone approached me that they wanna refer some of the content in their PhD thesis, and I was, astonished to see those comments. And I would love to have your feedback. Please share on all the channels. Thank you so much. And again, these are all as a disclaimer. These are our personal comments. It's nothing to do with any vendor or any customer or my current employer, or the previous employers. These are my own comments based on the research, based on the lifestyle, based on the documents which I read, and I usually put in the journals that, okay, whatever the reference document is. Thank you so much for listening and spending last, I think, around 7 minutes or 7.5 minutes to listening the intro or the overview. Now let's go. What we're gonna do today is we're gonna discuss what is gradient descent and how it works, and what types of gradient descent are available, or what type of are available. And these are primarily introduction, what is it, how it works, and what types of gradient descents are available. That's all, I think. So first off, topic is an introduction on this one, and that was one of my even tasks in my course, that, okay, we need to read and we need to understand what is gradient descent. And if you see it, it's the most widely used optimization strategy in machine learning and deep learning. Whenever the question comes to train data models, gradient descent is joined with other algorithms to ease and to implement and to make it understandable for all. And there's a common understanding that whoever wants to work with the machine learning must understand the concepts in detail. And what we're going to try is we're going to try to curate the information available with our different sources. And another important point is that I'm going to share 5 videos which are, from the experts on this blog, so that you can go and listen to that, which I also personally did it. And those are the gems to learn about the gradient descent, that how it is and what are the basics. I'm gonna just cover the overview, but those videos will be available, and you can go through in very detail from a mathematical point of view and from a machine learning point of view. And so as I said, this was one of the tasks in my course, and then I thought, okay, let's share with the rest of the community, my fellow colleagues. And there's always a question on the model's performance and to find out performance. Optimization is a technique used across the board or a standard method. Optimizing is focusing on how we can find out the best possible output from the model. It is also another way to check the preciseness of the output. In contrast to this, while you work in deep learning, you don't know the outcome you will get from the new data. Is this correct? Is this what you were aiming for? So question arises, what to do? There are various kinds of optimization techniques which are applied across various domains, like mechanics, deciding the surface of aerospace design, economics, cost optimization, physics, for example, optimization time in quantum computing. So optimization is as many more advanced applications like deciding optimal route for transportation. That's very common in the route or the supply chain or even the transportation management, or a shelf space optimization in the retail space. So many popular machine algorithms depend on optimization techniques such as linear regression, k nearest neighbors, neural networks, etc. The applications of optimization are limitless and is widely researched topic in both academia and industries. And that's what I think we are also doing as part of academia. So what we're going to see now, imagine if you use the optimization algorithm to train a model, you will get the performance outcome. In another way, it is the gradient descent which helps us to identify the parameters that minimize the cost function or prediction error. Gradient descent does this by iteratively moves towards a set of parameter values that minimize the function, taking steps in the gradient descent or gradient opposite direction. Now let's dive into the formal definition of gradient descent. So I thought, what is the formal definition on this topic? Now, and when you search it, you will find a lot of sources on the internet. But I went into the Wikipedia because that gives the primary definition and history of on this, who is behind this, and I like that one. That gives you all the flavor, all the background. So gradient descent is a first. I'm just reading as it is from the Wikipedia. So if you don't like to listen, you can go ahead and read it over there. So gradient descent is a first order iterative optimization algorithm for finding a local minimum of a differentiable function. To find a local minimum of a function using gradient descent, we take steps proportional to the negative of the gradient or approximate gradient of the function at the current point. But if we instead take steps proportional to the positive of the gradient, we approach a local maximum of that function. The procedure is then known as gradient ascent. Gradient descent is generally attributed to Cauchy, who first suggested it in 1847, but its convergence properties for nonlinear optimization problems were first studied by Haskell-Corey in 1944. So these are two men behind gradient descent. And if we will set the definition of only the word gradient. Now, a gradient is a vector valued function representing the slope of the tangent of the graph of the function, pointing the direction of the most significant rate of increase of the function. It is a derivative that indicates the incline or the slope of the cost function. So that's the definition of gradient. Now, what I understand, the word gradient means, if we simplify it, like, an increase and decrease in a property or something. Whereas descent implies the act of moving downwards. So in some simple words, or in other words, the observation done while coming down and reaching to some place and again moving up is termed as gradient descent. And this is a very, very well defined in an example with the mountain analogy, and we're going to do it on that one. So in normal terms, or as of the picture, it's as a slopeness of the hill. If you take an example of a mountain, and which we're going to cover in detail. And in this one, there is another very good correlation, which is covered in for to explain it, how the gradient descent work. So what in the Wikipedia, they took an hypothetical scenario, which is to illustrate or explain behind what is behind the gradient descent. So what the scenario is, like, take an example: a person is stuck in the mountains and he's trying to get down. That is trying to find the global minimum. There is a heavy fog such that visibility is extremely low. Therefore, the path down the mountain is not visible. It's very, obvious. So the person is stuck on the mountain. You want to go down. The fog is there, and the path is not visible. So they must use local information to find the minimum. They can use the method of gradient descent, which involves looking at the steepness of the hill at their current position, then proceeding in the direction with the steepest descent or downhill. So wherever you're standing, from that point you check the steepness and then start moving. If they were trying to find the top of the mountain, the maximum, they would proceed in the steepest ascent direction, uphill direction. I mean, if you want to go to the maximum, then you will walk upside. But if you go downhill, then it's the steepest descent. Using this method, they would eventually find their way down the mountain, or possibly get stuck in the same hole, local minimum or saddle point, like a mountain lake. However, assume also that the hill's steepness is not immediately obvious with simple observation, but rather it requires a sophisticated instrument to measure, which the person happens to have at the moment. It takes quite some time to measure the steepness of the hill with the instrument. Thus, they should minimize their use of the instrument if they wanted to get down the mountain before sunset. The difficulty then is choosing the frequency at which they should measure the steepness of the hill so not to go off track. In this illustration, the person represents the algorithm, and the path taken down the mountain represents the sequence of parameters setting that the algorithm will explore. Let's repeat this one. So in this illustration, the person represents the algorithm, and the path taken down the mountain represents the sequence of parameter settings that the algorithm will explore. The steepness of the hill represents the slope of the error. The steepness of the hill represents the slope of the error surface at that point. The instrument used to measure steepness is differentiation. The slope of the error surface can be calculated by taking the derivatives of the squared error function at that point. The direction they choose to travel in aligns with the gradient of the error surface at that point. The amount of time they travel before taking another measurement is the learning rate of the algorithm. See, that's how simply it's explained. The amount of time they travel before taking another measurement is the learning rate of the algorithm. So there is another, back propagation and limitations for a discussion of the limitations of this type of hill descending algorithm. The more details available. So that's how it defines the definition or the illustration of the gradient descent. Now, if you still imagine that you're at the top of the mountain, and that illustration was based on coming from you're stuck in the mountain, you're going to go to and then how you're going to find it. Now, take an example. If you're stuck in the mountain, again, I'm just taking it from a more different angles or point of view to explain it or to get understand. And frankly, this is for you and this is for me also. So I'm also learning it. So your goal is to reach the bottom field, or the bottom, or the down from the hill. But there's a problem. Another analogy, and I think I found it in another blog, and I will put it in the show notes. That in that it was mentioned as a fog, and then your goal is to reach the bottom field, but there's a problem. You're blind. How can you come with a solution? Well, you will have to take small steps around and move towards the direction of the higher incline. You do this iteratively, moving one step at a time until you finally reach the bottom of the mountain. So this is what gradient descent does. Its goal is to reach the lowest point of the mountain. The mountain is the data plotted in a space. The size of the test step you move is the learning rate. Feeling the incline around you and deciding which is higher is calculating the gradient of a set of parameter values, which is done iteratively. The chosen direction is where the cost function reduces the opposite direction of the gradient. The lowest point in the mountain is the value or weights, where the function's cost reaches its minimum. The parameters where the model represents more accuracy. That's frankly. So in a machine learning model with parameters, weights and biases and a cost function to evaluate how good a particular model is, our learning problem reduces to that of finding a good set of weights of our model which minimize the cost function. So that's how it defines the gradient descent from illustration purpose, that how you need to calculate it. And now we will go into the math point from a math point of view. And when I say from math point of view, and we are going to discuss, the very good resources, how it works. And I'm going to share with you another better way to explain it, how it works. I found it in the machine learning crash course from Google. And then another very good explanation is from my favorite source is Khan Academy on the gradient descent. And then another was one from the according to Deep AI. So we're going to read through, or we're going to understand from how it works from Google, Khan Academy, and Deep AI point of view, that how it's going to work. So as we understand, the gradient descent is an algorithm or that numerically estimates where a function output its lowest values. And that's as per the Khan Academy. And that means it finds local minima, but not by setting del of f or gradient of f equal to 0. Like instead of finding minima by manipulating symbols, gradient descent approximates the solution with numbers. All it needs in order to run as a function's numerical output, no formula required. This distinction is worth emphasizing because it's what makes gradient descent useful. If we had a simple formula like f of x is equal to x squared minus 4x, then we could easily solve del of f or the gradient of f is equal to 0 to find that x equal to 2 minimizes f of x, or we could use gradient descent to get a numerical approximation, something like, both strategies. And there's a full chart or the diagram is available on that one. And we don't have a simple formula for our function, then it becomes hard or impossible to solve gradient f of is equal to 0 if our function has 100 or million variables. Then manipulating simple symbols isn't feasible. That's when an approximate solution is valuable. And gradient descent can give us these estimates no matter how elaborate our function is. The way gradient descent managed to find the minima of function is easiest to imagine in 3 dimensions: x, y, z. Think of function of f of x and y that defines some hilly terrain when graphed as a heat map. And this graph will be available on the show notes if you want to refer to that one. But just imagine there's one graph and there's 3 axes, is x, y, z. We learned that the gradient evaluated at any point represents the direction of steepest ascent up this hilly terrain. That might spark an idea for how we could maximize the function. Start at a random input and as many times as we can take a small step in the direction of the gradient to move uphill. In other words, walk up the hill. To minimize the function, we can instead follow the negative of the gradient and thus go in the direction of steepest descent down. This is gradient descent. Formally, if we start at a point x0 and move a positive distance in the direction of the negative gradient, then our new and improved x, what look like, and it's mentioned on x of 1 and x0 to 5, del of function or the gradient function. So starting from an initial guess where x is 0, we keep improving little by little until we find a local minimum. This process may take thousands of iterations, so we typically implement gradient descent, with the computer and the machine learning. So that's how the gradient descent works in way. Now we will go into the types of the gradient descent, and now what I'm going to do I'm going to put the detailed videos how it works. Frankly, those are more expert videos rather than me, explaining it to you. So that's just like a reporter on how it works, so that it gives you the right content and the sources, so you can spend some time and understand it with the basic concepts. Now, what type of primarily there are three types of gradient descent algorithms, for small or large data sets, or which are commonly known or referred. And those are like a batch gradient descent, stochastic gradient descent, and mini batch gradient descent. And each has his lot of information material available from different university sources. And if we talk about how the batch gradient descent work, and it's the first basic type of gradient descent, which use the complete data set available to compute the gradient of cost function. If we need to calculate the gradient of the whole data set to perform just one update, or a batch gradient descent can be very slow and is intractable for data sets that don't fit in the memory. After initializing the parameter with arbitrary values, we calculate gradient of cost function using the relation that's, if you have records like 3 million records, you need to read it in all records into memory from disk, because you can't store them in all memory. So after calculating sigma of one iteration, we move one step, then repeat for every step. This means that it takes a long time to converge. And especially with the disk IOs and all that, those are bottlenecks. So then this inevitably require a huge number of reads. That both batch gradient descent is not very, very comfortable or right solution for large data, the huge data sets on that one. Then how the stochastic gradient descent works, it's turns out to be a slow batch gradient descent is look like a slower gradient or a slow algorithm. So for a faster computation, we prefer to use, or a lot of people use, a stochastic gradient descent. And the first step of algorithm is to randomize the whole training set. Then for updation of every parameter, we use only one training example in every iteration to compute the gradient of cost function. As it is uses one training example in every iteration, this also is faster for larger data set. And in stochastic gradient descent, which is called as it's commonly is SGD, one might not achieve accuracy, but the computation of results are faster. After initializing parameters with arbitrary values, we calculate gradient of cost function by using the inner loop, then taking the first step, pick the first training example, and update the parameter using this example, then for second example, and so on. So taking second step and then move on. So that's how until you reach to a global or a minimum, you will keep performing these steps. Similarly, the third one is the mini, which is called the mini batch gradient descent. So mini batch algorithm is the most favorable and widely used algorithm that makes precise and fast results using like a batch of M or batch of training examples. In mini batch algorithm, rather than using the complete data set, we usually do the iteration, a set of training or set of batch of data. To common mini batch sizes ranges between 50 and 256, but can vary from different applications. So it reduces the wide variance of parameter updates, which can lead to more stable convergence, can make use of highly optimized metrics that makes computing of gradient weight efficient. Some of these important points on this one is, so what it does, it takes the best of both worlds and performs for every mini batch of N training or M training examples. It reduces the variance of parameter updates, which can lead to more stable convergence. It can make use of highly optimized metric optimization, common to state-of-the-art deep learning libraries, that make computing the gradient with respect to mini batch very efficient. Common mini batch sizes, I've already mentioned 50 to 20, 56. And mini batch gradient descent is typically the algorithm of choice when training a neural network, and the term SGD usually is employed also when mini batches are used. And in modification of SGD, in the rest of the we can or share with you. There is another very very good paper written from Sebastian Ruder, an overview of gradient descent optimization algorithm for Insight Center of Data Analytics, NGI Galway. I think it's for the university. It's shared the paper on online and Cornell University. And if you read this paper, it has a strong and very detailed introduction on the gradient descent, batch, stochastic, and then mini batch gradient. What are the challenges from a deep learning or machine learning point of view? Then even gradient descent optimization algorithms. So there are another key point is on the algorithms. Optimization algorithms which are talking about momentum, which so with this now I will share with you the 5 very exceptional videos which I like. I shared with you the videos from very very strong resources like Andrew, Khan Academy, and from the deep learning on gradient descent, how neural networks learn, and then our favorite from the Josh Strummer, step-by-step gradient descent. And in short, if we summarize the situation with the gradient descent algorithm, is an optimization algorithm which is used to minimize the objective function. And with the machine learning, the objective function that needs to be minimized is termed as cost function or a loss function. So gradient descent is used to minimize the loss function or a cost function in machine learning algorithm, such as linear regression, neural networks, etc. Gradient descent represents the opposite direction of gradient. Gradient of a function at any point represents direction of steepest ascent of the function at that point. Batch gradient descent is operating the weights after all the training examples are proposed. Stochastic gradient descent is about operating the weights based on each training data or a small group of training data. And gradient of a function at any point can be calculated as the first order derivative of that function at that point. So that's just a summary on the gradient descent, and it is it is one of the most common algorithm, and this post was an introductory, and this has been working hard for deep learning optimizations when this gradient descent was even as a first paper, and there are so many papers available on the gradient descent with respect to machine learning. And whatever I got a chance to review and read, what I will do is I will put it in the show notes, and I think invite you to come and read and study along with me. That's the way we will learn from each other and improve ourselves. Thank you so much for listening and for your weekly podcast with the only objective of learning and sharing. Thank you so much, and have a blessed day. I think holiday season is coming, or all the way December, and then we are gonna start on working on New Year resolutions and all that. Have a blessed life. Thank you so much, and please do keep share your feedback, comments. Thank you.
Thanks for listening to the O Tech Talks podcast, and be part of Tech Talks at otechtalks.tv. It's a turf to share ideas, insights, and innovations.